Given three colors red, green, and blue, if you are asked to paint the faces of a cube, how many ways are there to do it? Well, for each face we have three choices of colors, and there are altogether 6 faces of a cube, so the total number of ways should be 3 to the 6, or 729 coloring patterns. However, what if we count any two colorings the same if one can be transformed into another by a rotation, so that even though these two look different, we still count them the same? With that consideration in mind, the question of how many ways of coloring becomes more difficult. This kind of counting problems where we consider symmetries is not only applicable in this mathematical investigation, but also notably in counting the number of isomers of an organic molecule, because apart from the letters Cl upside down, the molecule after rotation is the same molecule. A perhaps less expected application is in music theory, where we count the number of 3-note chords, or trichords, where chords obtained via transpositions and inversions are considered the same. But we will leave these non-mathematical applications for another video. Before we tackle all these questions, we need to first revisit orbit stabilizer theorem in chapter 2 of the video series on group theory on this channel. Let's say we have a group G acting on a set X, and here we illustrate the set X as these dots. Let's say we pick this dot as little x, then we will define its orbit to be where little x can go under the action of symmetries, so all it contains has to come from the set X. On the other hand, symmetries that fix X form the stabilizer of X. The orbit stabilizer theorem simply states that the product of the sizes of the orbit and the stabilizer is the size of the whole group. The proof is basically this flowchart, which is fleshed out with much more detail in this video. Here is one simple fact about orbits that we will need. Let's say these dim spots represent elements of the set X, and pick an element to be our little x. Let's say these bright spots represent the orbit of X, or where X can go, and pick one of these spots to be called X star. What is the orbit of X star? Can it say go to some other bright spots as well? Of course, we can first go back to the little x, then go to the bright spot that we want. This is because, by definition of being in the orbit of little x, there is at least a symmetry to get x to each of these two spots. For the first step, we just revert the symmetry, and keep the symmetry for the second step. Basically, that means the orbit of X star at least includes every bright spot. What about some dim spots? Can X star go there? No, because if X star can go there, then little x can also go there, which is not possible because the dim spot is not in the orbit of X, so X cannot go there. So the orbit of X star is exactly the bright spots, no more, no less. If we pick X somewhere else instead, then its orbit would be different. Eventually, everything in the set would belong to exactly one orbit. With a bit more knowledge about orbits, let's see what we actually want. We want to count the number of ways to color a cube with symmetries in mind. The natural action to take is to let the group of all rotational symmetries of a cube act on the set of all the possible colorings. Representing the set of all colorings as these little dots, what does being in the same orbit mean? Or what does being able to transform from X to X star mean? Because G is the group of rotational symmetries of a cube, that means we can go from X to X star via a rotation. But we say that we would count them the same if one can be transformed to another by a rotation, so the entire orbit represents the same coloring. The same thing applies in other orbits, so counting the number of colorings means counting the number of orbits in group theoretic terms. So we will now focus on counting the number of orbits. We will use a trick to find the number of orbits, which starts off by lining up the elements of X, as well as the symmetries in the group G. Then we start to draw some lines between G and X, but with the criterion that we only draw lines between little g and little x if the little symmetry G does not move little x under the action. So for example, if this is the identity symmetry, then by definition it fixes everything. So we will draw lines from this identity symmetry to every element of X. After we draw all the lines, we want to count how many lines we have drawn. There are actually two ways to count. The first method is to count the number of lines from each symmetry in group G, then add them all up. But we need to first understand what each number we are adding actually means. Based on the criterion on how we draw the lines, these numbers are the numbers of the x's each symmetry fixes. In this case, it fixes this green dot, and we call the collection of things that is fixed by G the fix of G. So each number here represents the size of the fix of G, and we are summing up all these sizes of the fixes. But there is another way to count the total number of lines, which is counting the number of lines to each element in X, then adding them up. However, instead of adding them individually, we add them in batches. We are going to have the subtotal by counting everything from the same orbit, then adding the subtotals up to get the grand total. Because of the criterion to determine how we draw the lines are drawn from the stabilizers. That means each element contributes exactly the size of the stabilizer to the subtotal. The reason why we consider subtotals first can be seen from the orbit stabilizer theorem. Everything inside the orbit has the same orbit, so their orbit sizes must be the same. This in turn means that their stabilizer sizes must also be the same, so each element in the same orbit contributes equally to the subtotal. Since the number of elements in the orbit is precisely the size of the orbit, we multiply by the size of the orbit to get the subtotal. This is precisely the size of the group G by the orbit stabilizer theorem. Using exactly the same argument, every orbit will contribute the size of G as the subtotal. So the grand total is the number of orbits times the size of the group. Because these two expressions come from counting the same thing, they should be equal. And by simple rearrangement, we can get the expression for the number of orbits. This result is known as Burnside's lemma, the topic of this video. Let's go back to the original problem. We want to find the number of orbits under the action of rotations on the set of all colorings of a cube. Let's look again at the formula from Burnside's lemma. The first thing we need to evaluate is the size of the group. Of course, you can list them all out, but in practice, it is very likely we miss some symmetries, so we can use orbit stabilizer theorem, but on a much simpler action. Instead of acting on the set of colorings, we simply act on the faces. In this cube, we pick this top face as the little x. It is not difficult to see that x can be rotated to any other face, so the orbit size is 6. Symmetries that fix this face would contain only the rotations around this axis, which are precisely identity symmetry or rotations of a multiple of 90 degrees, which means the stabilizer has size 4. So by orbit stabilizer theorem, the size of the group of rotations is 24. Now we need to find the fixes of symmetries. Let's first consider the fix of the identity symmetry, that is, no rotation at all. Then it fixes every coloring. So its fixed size would be the size of the whole set of colorings, which is 3 to the 6, where 3 is the number of choices of colors for each face, and 6 represents the number of faces of a cube. Anyway, let's move on to another symmetry that actually involves rotation. The simplest is a rotation about this axis. First, we think of the rotation by 90 degrees, clockwise or counterclockwise. What does this rotation fix? If this face is red, and we are considering such an anti-clockwise rotation, the face on the left would be rotated to the red face, which means the face on the left has to be red in the first place. Using the same argument, all 4 lateral faces of the cube must also be of the same color. There are no restrictions on the top and bottom faces, so the fixed size is 3 cubed, where the base denotes the number of colors available and the exponent denotes the number of faces that we can actually choose colors. That is the top and bottom faces and 1 of the lateral faces. But there are 3 such axes, and for each axis, we can rotate 90 degrees either clockwise or anti-clockwise, so we need to count this 6 times. The rest of the argument works in a similar way, so I will walk it through with a little bit less detail. Using the same 3 axes, we can consider the 180-degree rotation. It turns out the fixed size is 3 to the 4, because we can freely choose the colors for the top, bottom, and 2 of the 4 lateral faces. Next up, we have rotations about the long diagonals by 120 degrees. This refers to rotation along this axis. Since there are 4 such axes and we can turn 120 degrees clockwise and counterclockwise, there are 8 such rotations. It turns out the fixed size is 3 squared because faces around a point needs to be of the same color in order to be fixed. The final category of rotation axis passes through the midpoint of opposite edges, which refers to rotations like this. There are altogether 6 such axes passing through each pair of opposite edges. So there are 6 such rotations because one axis only corresponds to one rotation. It turns out the fixed size is 3 cubed because we can choose the colors for 3 of the faces, then the rest has to follow. The final step is to add up these fixed sizes, considering facts like there are 6 90-degree rotations, so we need to multiply the corresponding fixed size by 6, and so on. The total now turns out to be 1368. Putting this directly into the formula, we see that we also need the size of the group G, so we put that 24 in as well, and we get 57. So the answer to our original question, the number of rotationally distinct ways of coloring a cube when we are given 3 colors, is 57. However, this is just a very classic example of using Burnside's lemma. It does have applications in a non-mathematical context like organic chemistry or even music theory, but we will explore those in another video. In any case, do consider leaving a comment if you enjoyed this video, and don't forget to subscribe and hit the bell because my upload schedule isn't too consistent, but when I upload, it should be good stuff. See you in the next video. Bye!